Alright, so our goal, as I indicated earlier, is we're going to move through the material we learned at the beginning of the semester, but now rotationally rather than in a straight line. And before we can move from our kinematic equations into force, like we did at the beginning of the semester, we need that junction between the two, which was mass. However, let's think about this for a second. If you have a top-loading washing machine and you put a giant converter in it on just one side of the agitator and turn the washing machine on, you end up with a problem. The washing machine starts rocking back and forth and making a giant mess. Versus if you take that same converter and neatly wrap it around the agitator, then typically the washing machine rotates smoothly and your laundry gets done. So how mass is distributed in a system when it's rotating matters. And the term that we use to characterize how mass is distributed in the system when it's rotating is moment of inertia. Moment of inertia is represented by the capital I. And whenever we're calculating moment of inertia, we have to take into account everything in the system that is rotating. So moment of inertia of a system is the sum of all the individual moment of inertias in the system that are rotating. Now, how we do that is going to depend upon what our system looks like, of course. So the first shape we're going to discuss is a point mass. And a point mass is a small mass where essentially you can ignore the volume. So for a point mass, how you calculate the moment of inertia depends upon the mass of the point mass and the distance the mass is from the rotation point. And we're going to square that distance. So it's getting in that concept of you have a mass and it's distributed over a certain distance from the rotation point. Now we could think of all objects as being made up of point masses. You can think of all objects are made out of atoms, which definitely would be a point mass, and they would all be some distance from the rotation point. But that would get really, really complicated because you can think about how many atoms an object would be made up of. And that each atom would be a slightly different distance from the rotation point. So that would be a lot of addition. So instead, we have some pre-made equations that take into account how that mass is distributed in the system. And those are linked in the constants table link in the left-hand menu in Blackboard. And this is something I would provide as part of the information I would provide on the exam. So just keep in mind, whenever you have different objects of different shapes rotating in a system, they're going to have different moment of inertia equations. So let me highlight this below. At the bottom here we have a solid sphere with 2 point masses attached. So since we need to sum all of our moment of inertias and equations, I first added in the 2 point masses, and then I went to the table provided in the constants link in Blackboard, and I found out that the moment of inertia equation for a solid sphere is 2/5 mr squared, where in this case the capital M is the mass of the sphere itself, r is its radius. Now over in our moment of inertia equations for point masses, the r value, which is the distance from the rotation point, also happens to be the radius of the sphere in this case because the rotation point's at the center of the sphere and they're along sort of like the equator of the sphere. So the distance between these two would be the radius of the sphere. But that's just a coincidence in this case. Over here, notice I didn't fill this one in. This is a hollow spherical shell. And if we want to find the moment of inertia of this rotating system, assuming this is our rotation axis here, we still have the 2 point masses, but since this is a thin spherical shell, the moment of inertia equation is going to be 2/3 times the mass of the sphere times the radius of the sphere squared. So there's a difference between 2/5 and 2/3 here. And that takes into account the fact that there's mass inside of the sphere that has changing distance from the rotation point, because there's some mass that's really close to the rotation point and some mass that's farther away from the rotation point, versus here with the thin spherical shell, there isn't much difference between the distance between individual particles and the rotation point because it's along a thin shell. So you're going to get a different value for your moment of inertia for this situation compared to this situation. So once again, I reiterate, whenever you're calculating moment of inertia, you need to analyze what shapes you're working with and make sure you find out what the appropriate moment of inertia equation is.